Computers are, getting these presentations together is always a challenge. But I'm sure Don will figure it out.
Yeah, I think, okay, yeah,
He's getting it set up, I believe, for the online people.
yep,
Yeah.
it's recording.
Oh, recording, okay.
There you go.
Okay, well, first of all, thank you all for taking the time to come and listen to me. I did not expect a crowd that was quite this big. But I always enjoy talking to people and telling them what's happening with quantum and trying perhaps to give them some understanding of what it is. Some people think it's magic. It's not quite magic. There's a lot of science behind it, and I'll talk a little bit more about that. As Stefan was saying, my company is called Global Quantum Intelligence. We're a team of about 18 people that is the leading market analysts for the industry. We work with governments. We work with the big quantum companies, some of the three-letter companies that you might know. We work with startups, venture capitalists, and we advise them with regard to how to get involved with quantum, how to be successful in quantum. For startups, we do things like due diligence reports if investors want to do that. So I always enjoy talking to people about what we do and, of course, about the industry. We are, as I said, we're a worldwide organization. I'm the California guy. We do have another person here in Los Angeles, but we are worldwide. We have people on the East Coast. We have people in Europe. We have people in India. We have people in Japan too. So it's important because quantum is a global industry. It's not US only. There's a lot of very, very good activity happening, particularly in Europe and in China. So let me start. I'm going to start, the first section of my talk is going to be on the basic principles of quantum computing. There's a lot of things that come into play here, and it really started 100 years ago there was a conference. There's a quantum. It was called the Solvay Conference, which was happened in 1927, where Einstein and Bohr and Schrodinger and a bunch of the top physicists in the world came together, and over the next several years, they developed some new concepts with regard to.
I think we're not sharing the slides.
Oh, you want to? We're not sharing the slides. You want to?
Yeah.
You want to fix that?
Yeah, let me fix that.
Okay, we're going to take a quick break here so the online people could see the slides. There.
Yep, good. Thank you.
Okay. I guess that's good. And they came up with some new concepts, new physics called quantum mechanics that we had previously not known about. And what is interesting is that some of those concepts were not really leveraged in the computers we have today, even in our latest cell phones, the big computers, even the GPUs that are used for AI. They don't use these concepts right now. And what's been happening really over the past, let's say 15 years, is researchers at universities and later on a few companies have said, we could make more powerful computers if we can figure out how to leverage these new concepts in physics and do computation in a different way. And that's what I'll talk about over the next few minutes. So Okay, Don, the clicker's not working now.
Always something.
Okay, there we go. Okay. So the thing that's interesting is that these are non-intuitive concepts. You don't really see them in the day-to-day real world that we live in today. And that's because for the most part, with the exception of the fifth Nobel Prize, which I'll talk about a little bit later, they happen at the micro level, at the electron level or the individual ion level. And at the macro level that we all live in, we don't see those things. So I'm going to talk about those. There was a famous professor at Caltech. His name was Professor Richard Feynman. He had a funny quote. He said, if you think you understand quantum mechanics, you don't understand quantum mechanics just because it's non-intuitive. But I'm going to go through three of those and talk to you a little bit about what they are and how they can be used subsequently to build much more powerful computers. So the first one is called superposition. I think everyone in this room is probably familiar with a bit. You know, it's either 0 or 1, the binary system. All the computers that you've been using today are based on that. There is there is something called a qubit, stands for quantum bit, which can actually be in a state of both together at the same time. It's called a superposition of 0 and 1. And that actually allows you to multiply the power of your computations. And I'll show you a little bit, some examples of that in a slide coming up. The other, and this is really strange, it's called entanglement. Think of two qubits, which are like twin brothers, and they can almost like read each other's minds. You can put them in a state, either both in 0 state or both in 1 state or something like that. You can physically separate them. You could take one and put it on the moon, and if you change the state of the first one at the exact same time, it'll change the state of the second one too. So that is called an entanglement. It is a very interesting property, and you can see in the slide here where it says observed here, affected over there. That is one of the things that people use, for example, for quantum communication, to be able to transmit cryptographic keys from one place to another without anyone intercepting that. It's a very unusual thing. A third thing is called interference. I don't know if you study it, maybe Mr. Pelosi has talked about that, but there's something called a very famous experiment called a dual slit experiment, where you shine a light through the first screen. First screen has 2 slits, and then you project it. You project it against like a wall or a screen or something like that. And what you would expected was that, I'm going to walk over here a little bit, that the way the things from this would just cover this and sort of be, sort of look like this, at the very middle of the direct aim, it would be brightest and then would gradually go out, and you can do that on the second one. But if you do this experiment, and I think Don is actually, as a kid, he could show it to you sometime later on, what you end up with is something different. And people didn't expect this, where it's bands of dark and light, dark and light, dark and light. And this experiment actually proves that light is actually can both be a particle as well as a wave. And these red lines here show the waves and how they do. And what happens is when, and maybe you've seen this, if you go to like a lake or something and you throw two stones in the lake and it creates waves. When the two waves meet, that is like the peak. We're called constructive interference. But if you have the peak of one wave and the trough of the different wave, they cancel out each other, and that's called destructive interference. So that's a concept that's used in quantum in order to sort of filter out the right answer in your calculation. There's one, I guess I'm missing a slide here. I'm going to go back. There's this thing called tunneling, and this is related to that Nobel Prize. It is used in something called flash memory, where you can have a barrier, and in a little chip, it might be a barrier of silicon dioxide or something like that. You can have electrons on one side of that barrier, and those electrons can, even though that's supposedly a barrier you can't walk through, the individual electrons can go through that. It's called tunneling. And that's actually what the Nobel Prize was related to. And that's actually used, that is one of the things that is used in your cell phones. The memory in your cell phones, the memory, a lot of the memory that's in there, to store your stuff on a long-term basis, even when the phone is off, uses this thing called flash memory. So tunneling is used in a certain specialized type of quantum computer called a quantum annealer that I'll mention briefly. But anyway, the experiment that won the Nobel Prize yesterday had to do with the fact that this team of 3 people not only demonstrated tunneling, they demonstrated it on a macro basis. So, and people thought it was impossible to show that on a macro basis. They thought it was only applicable when you do it for individual electrons. I know that I can't walk through a wall. I can't tunnel through a wall. I'm just too big, but they were able to come up with a experiment that did demonstrate large scale tunneling. Okay, to superposition, entanglement, and interference. So specifically, these 3 things, superposition, entanglement, and interference, those are concepts that have not previously been used in what I call classical computers. And those are the computers that are based today. Fundamentally, the computers we have today, even your cell phones, are all based on physics principles that were discovered in the 19th century. Things like Ohm's law and the electron and those things, Boolean logic, those are all discovered in the 19th century. And then in the early 20th centuries, 1940s, the first classical computers came out. But the computer scientists didn't use these principles that I just talked about. Now, there are challenges in using them, and that's why it's been slow to develop. But the fundamental concept of quantum computing is the fact that you will start to create computers that leverage these 3 things, and you can create machines that are much, much more powerful in terms of what they can compute for certain problems, not everything, but for certain problems that you had never, ever been able to do before. And one of the reasons is that quantum computing can hold, it's called a qubit, can hold an exponential number of states. If you look at this chart here, if you just look at, this is a chart that shows what information can be held in 2 bits or two qubits. How many different states can you represent under those 2 circumstances? So 2 bits, we know it, you can have 4 different states. 0.00011011. But in a qubit, remember I said a qubit can hold, a qubit can be in 0, it can be in 1, and that's what's shown in the top 4 lines of this. But if you start utilizing this thing called superposition, you can have, was it 5 additional states where you could have the first qubit, let's say, as a superposition of 0 and 1, and the second qubit is a 0, or 0, another superposition and 1, or you can put the second qubit into superposition and the first one can be 0, or they both can be in superposition. And that the one where it's both in superposition is shown at this one at the very bottom here. And right here, on the right side where it says the square root of 1/4, this actually is the way that the quantum scientists show this type of thing. All this, there's mathematics that behind all this. Most of quantum computing is described with matrix math. This would be, these are all vectors or matrices. Anyway, and then finally, if you want to then take advantage of the entangled state, you can have this. So here, at the very beginning, I said the 2 bits can be in 4 different things. Here you have 2 qubits that can be in basically 15 different states, as I show it there. So that is one of the secrets that allows people to greatly expand the power of quantum computers. So, the one thing to understand about computing in general is no matter how powerful a computer you build these big data centers, and maybe you've seen newspaper articles about that, which may have racks and racks, and may have tens of thousands of microprocessors inside those. That's still not enough power. The scientists and the researchers always have problems that exceed the performance of even the largest supercomputer. And actually, this is a very simple problem, but it's quite often taught in computer science. It's called the traveling salesman problem. And here the problem is that you have this little salesman, and he's going to drive from city to city. He has to cover all these different cities and visit customers and give his sales pitch. And the problem is, or what he wants to do is figure out the shortest path. He doesn't want to go, for example, from Atlanta to San Francisco, and then back to New York, and then up to Chicago, and down to Texas, Boston. He's going to have large amounts of driving to do. He wants to find the order to visit each one of those systems that gives him the least amount of miles on his car. It turns out that if you submitted this problem to a computer, it's easy to do if you have 4 cities or 5 cities or 6 cities. The number of combinations is actually factorial. If you have 4 cities, it's 4 factorial. If it's 10 cities, it's 10 factorial. But if you ever plotted, you can do this on your cell phone. I actually was doing it earlier today. If you tried to put in 100 cities, your cell phone is going to go overflow. It's over 10 to the 157th power. That's a 10 with 157 zeros behind it. And that's a problem. That's a problem that just can't be calculated. Poor guy, the best he can do, the best the computer science people can do is they do have programs that make some estimate. They give them an approximate route that probably is going to be fairly close, but they can't calculate. If you have 100 cities, the computers can't calculate for certain which is the best route. Even though, they know the algorithm how to do that, they just don't have the computing power to do that. And that's where quantum really comes in. There are a lot of problems like that, and I'll talk about it in a few minutes. But logistics is actually one of those areas. So the reason quantum computing win is as follows. I just talked about the traveling salesman problem, where you have 3 cities, 5 cities, 10 cities, and it's easy to do. It's easy to do when it's a small number. But what computer scientists look at is, how does the computation complexity increase as you increase the number of items that are involved? So the traveling salesman problem, it's the number of cities. If you want to simulate chemistry, let's say you want to simulate a molecule, it will increase the more atoms you have in that molecule, the more complex the simulation is. So the computer scientists, they have this graph, and again, this is shown, and they have various problems, and they say, how does it increase as the number of items increase? And there's something called, it could be linear. For example, if you have a list of items, an unordered list of items, and you want to search that list to find a match of some type, the amount of time the computer is going to take is going to be basically a linear function of the items in the list. In other words, if you had a list of 100 items, again, unordered items, and of different items, and you had one that you wanted to find a match. If the list is only 25, that'll take you a certain amount of time. If the list is 50, it's going to take double the amount of time that it took for 25. And if it's 100 items, it's going to take 4 times. So that's called a linear increase. Other things are called polynomial increases. So that would be like n squared, or the one that's a really killer for classical computers is what's called exponential scaling. So if you have a problem where the number of computations you have to do to solve it is exponential, and exponential would be like 2 to the nth power, that grows very, very rapidly. And that's really shown here by this curve that's classical. And what's interesting is that if the number is small, as shown here, the classical computer will always beat out the quantum computers, because a basic computation, like a basic gate in a quantum computer, is about an order or 2 orders of magnitude slower than a basic computation in a classical computer. But where quantum wins is the fact that the computer scientists have figured out algorithms that allows you to take those problems that have this exponential scaling and figured out how to do it with a quantum computer such that it's maybe linear or what's called polynomial scaling. So here, again, when it gets really, really large, you can see the classical is off the charts, and then the various types of quantum computers are much, much lower, can be solved much, much faster, much less resources. So that's the reason that quantum computer wins. But I will caution you and say that it is very dependent on the problem. You're never gonna, check your email or browse the web with a quantum computer. It's for very specific problems, again, that I will talk about. Now, there are some challenges with quantum computing, those things that I talked about. And one of the big challenges right now is reliability. So the reason that quantum computers are not, around everywhere today is the fact that they fail quite often. It's sort of like if you wanted to drive a car from here to New York and you get a flat tire every 10 miles, it's going to take you a long, long time to get there. So these qubits are very, very fragile. And they're also very, very sensitive to the external environment. You can put them in one of these states, the superposition state, remember, where it's like a 0 and 1 at the same time. And sometimes, actually, a lot of times, they'll what's called decohere. They'll fall back to a 0 state, and it's no longer useful if it goes back to the classical state. So the thing that a lot of people are working on is what's called quantum error correction, and that's or fault tolerance, where people have come up with codes, and I won't get into details today. Maybe we'll come back and I'll talk a little bit more about that. But what you can do is to combat the problem that these quantum computers are fragile and you put them in a state and they only stay there for so long and then they collapse. The computer scientists have come up with schemes where you take a collection of qubits, what are called a collection of physical qubits. You take maybe 100 of them, you put them in some state, and the collection of those represents what's called a logical qubit. And that's what's shown here. This, and that is, if you can see it, that's the gray curve here. If you don't do that, you can also use quantum computers without error correction, and that's called NISQ. That stands for near-term intermediate scale quantum. That's what's shown on this chart. But error mitigation is a big effort. I tell people, for any of you who want to go to school and study something and be assured of a job, a quantum error correction engineer is the hottest job right now in the industry. So where are we today with quantum? The industry, the capabilities of the computers have been growing very, very fast. When I actually started the Quantum Computer Report 10 years ago, actually in 2016, IBM put the first quantum computer on the web. It had 5 qubits. Today, they have in high volume production a quantum computer with 156 qubits, and they have a roadmap. By 2033, they'll have 100,000 qubits. So the hardware capabilities are expanding very, very fast. At the same time, the software capabilities are improving. The software is getting easier to use. It's getting more powerful. It's getting more optimized. And the way, I show it is with this little bridge here. This is a picture of the Sydney Harbour Bridge when it was being built. It's a very famous bridge in Sydney, Australia. And in order to achieve what the industry calls quantum advantage, where users, enterprises are using it on a daily basis. Pharmaceutical companies are using it to develop new drugs, or companies like Federal Express are using it to route all their delivery drivers, or those types of things, or people are using it to train AI. That's what I call quantum advantage, and I've written many articles about that. But where we are here, we're really not quite there yet. We're close, but you need to have improvements on both sides. You need to have improvements on the left side from the hardware guys to make their computers a little bit more powerful, more qubits, and higher quality qubits. And one of the things we get from all the manufacturers are these things called roadmaps, where they say we're going to have, this is hypothetical. We'll have 150 qubits today. In 2026, we'll have 300 qubits. In 2027, we'll have 700 qubits. In 2030, and they all have engineering schedules and engineering plans to do that. And of course, the more qubits you have, the more capable the computers are, the more powerful. But at the same time, the software guys are doing the same thing. And when those two meet, then you'll be able to cross that bridge and get quantum advantage. And you'll start seeing an economic payoff. Billions of dollars have been put into the industry, both by governments and venture capitalists. And I remind people that this is not you're not doing your job at the when I talk to people at the quantum companies to just write a new paper for Nature magazine or the physics magazine. At the end of the day, you want to create something that people could use and benefit from, which will translate into revenue for a company or maybe lower cost for a company and increase profits. So I'm going to talk a little bit about who's playing in it and the different types of qubits they have. We track over 400, 500 companies between hardware and software that are involved in the quantum industry. And we segment them in terms of, I guess this doesn't, let me see if this, oh yeah, it does have one. Okay, we segment these in terms of different types of companies. So there are companies we call the quantum majors. And some of these are companies like IBM, Google, Microsoft, as well as some fairly large startup companies called PsiQuantum, Continuum, those types of things. NVIDIA, who makes the GPUs, they don't make quantum computers, but their chips are used to support quantum computers as components. AWS is Amazon. I know probably everyone here has bought stuff at Amazon. What you may or may not know is Amazon has a big business running data centers, and a branch of that business is called AWS, Amazon Web Services, and they're developing quantum computer in Pasadena, as well as Japanese companies, those types of things. We have a lot of startup companies, both here and in Europe, that are developing the quantum computers. And we have more that are that provide various services and those types of things. A lot of the quantum computers are being accessed over the cloud, so that, for example, I could log on to the Amazon system, for example, and I could write a program on my laptop. I could send it to Amazon, and then or one of these companies, they will process it on their quantum computer and then send the results back to me. The PaaS stands for platform as a service. And then you have a lot of emerging companies and many, many startups. And overall, we have 300, 300 or 400 of these companies out there. The other thing that we're also tracking, which makes things interesting, and this is where it's perhaps relevant for people interested in photonics, there are many ways of building a qubit. There's a lot of different technologies. SC stands for superconducting circuits. So you may have heard or you may have studied this phenomena called superconductors, where if you take a metal and take it down to very, very low temperatures, under maybe a few Kelvin or a few millikelvin, the conductors lose all resistance to electricity. And a very strange thing, but people have been able to make qubits using that as a phenomena. There's something called trapped ion. So an ion is an atom that's missing an electron. So it has a charge on it. But people can use those, they can manipulate those to do the various quantum gates and do the various operations. Those trapped ions are typically controlled by lasers. So and that's where photonics comes in. I visited many of these companies, and I walk into their lab and I see a giant table with a bunch of lasers and mirrors and beam splitters and all sorts of stuff like that. And that's what they use to manipulate those ions. There's something called neutral atoms. Neutral atoms, somewhat similar to a trapped ion, except it's neutral. So the electron is back in there, and electrons and protons match. But people can still manipulate those and use those. There's something called optical tweezers, where you can use lasers to move around atoms at the individual atom level. And then you can use beams of light. The companies like Quantum, for example, they've received $1 billion, and they're building a very large quantum computer. One is in Brisbane, Australia. Another is in Chicago, Illinois. And it's a company. Their headquarters is in Palo Alto, but they are using beams of light with various interferometers and those types of things to build these things. And then you have color sensors. Someone was mentioning NV Diamond. We have those color sensors. Silicon spin. I actually, there was a conference on silicon spin this morning that I actually came from. It was in Rancho Palo Verdes. The Hughes Research Lab, HRL and UCLA sponsored the conference. So you can use a single electron as a qubit, and electrons can have this thing called spin. It's called spin up or spin down, which creates tiny magnetic fields, and people can use those as qubits, and various other things that are out there. So there are many ways of building a quantum computer, and there are many companies competing. One of the things that's really, really interesting about this industry is it's like a horse race. You got all these players that are trying to come up with the best quantum computer, and we don't really know who's going to win. So that's one of the things that our company tracks on a daily basis. Now, the rest of this talks about the various components of how you build a quantum computer. And I won't go in some of the challenges that they are, but it starts with at the chip level, the substrate and the chip, and then goes through how you connect it all together and goes all the way up to what the architecture is, how you build it. But the important, and what we've done in our company is each one of these technologies we've looked at from the standpoint of each one of these individual items that are sort of the challenge. And we've color coded it in terms of how mature it is. Green means it's very mature. Pink means, or blue means it's pretty good. And then pink means there's still a lot of work to do. So as you can see, no one has a solid column of green right now. And that's why there's hundreds and thousands of people who are all working at these companies trying to solve those problems. And some of them are working very, very hard. So a lot of things have to happen to achieve this thing that I call quantum advantage. And I talked a little bit about them. You have to, you start with the users. The users have industry problems. I'm Pfizer. I want to develop a new drug for cancer or something like that. They come up with a use case. They have to figure out what type of quantum algorithm they can use to solve that. And then what are the various platforms they can use and the things they can use. And then, on the blue is some of the things that the quantum companies have to put together in order to help them solve that. So at the very end, you'll have something that solves your problem. And again, the different solutions we can show here on the end there are different types of quantum computers, or really different maturities. There are a few problems that we believe will be able to achieve quantum advantage without error correction, without fault tolerance. And again, that's what NISC is. And that's, I think, what you'll see. Actually, the computers we have today, they're all NISC, actually. None of them are really powerful enough to do something that classical computers can't do. But the timeline that we believe is that within the next 2 to 3 years, as these NISC computers get more and more powerful, they will start doing things that the classical computers can't do. And then as we progress, FTQC stands for fault tolerant quantum computer. Again, that's where you use error correction. And that's what's going to be the limiter of NISC is you don't want to submit a problem to a quantum computer, and then in the middle of the calculation, the qubit has an error, and at the very end, you're just going to get garbage out as the answer. And you know, for folks like us who deal with classical computers, the hardware itself very, very rarely fails. The hardware is you know, a typical transistor, for example, will work 99.99999999999% of the time. In a qubit, qubits you're lucky if you can get a qubit to work 99% of the time. So that's why you need this error correction. So, but error correction will also go through phases. A little bit of error correction is called early FTQC, fault tolerant quantum computing. As they go on, they'll get more sophisticated, more qubits, and there'll be large scale quantum computing. This tech shows a little bit about the market. You know, we had data. Let me just click through this a little bit. We had data that the global gross domestic product, see if I can read it here, is $95 trillion. And this is 2021 throughout the world. And this is actually an analysis from economists in terms of how that global gross domestic product segments between various industries, between retail, private services, business services, transport, recreation, construction, et cetera, as well as things like manufacturing, chemical materials, and industrials. And what our analysts have done is in each of those industries, we have this little icon that shows the different type of quantum applications that would be applicable to that industry. And so these are the use cases from cryptanalysis to simulation, machine learning, optimization, advanced protocols, position navigation, timing, sensors, that type of thing. And this shows where it could be used. In general, we're saying that, although I was saying earlier, quantum computing is only useful for some applications, but it's useful, every industry has a potential use for quantum computing in at least one instance. So there's a really, really large economic potential where people are talking that the benefit of quantum computing over the next few decades will be measured in the billions and trillions. And that's why, of course, the venture capitalists are investing in these companies. And that's why the governments are investing billions of dollars into quantum. This is a chart that we have that is our analysis that shows what countries are investing. United States has been investing, and this is the United States government, or investing 5.3 billion in terms of research grants. A lot of that money is going to universities, for example, as well as private companies. The big one actually is China. Where's China? $16 billion. But Europe is also very big spenders. UK is actually spending almost as much as the US. Germany is 3.7 billion, France 2.5 billion. So all these companies worldwide they see the potential of quantum, and they're making investments. They're giving grants, and of course there's a competition here also, and they all want to be they all want to beat out the United States. So we'll see if they can do that. Right now, the U.S. though is the leader. And then there's public markets also, as well as venture capital. If you studied the stock market at all, there are now a handful of quantum companies that have gone public, which means you can buy their stock on the stock exchange. Companies like Ion, the company's names would be IonQ, Rigetti, D-Wave, Arcit, Quantum Computing Inc. And what's interesting is those companies have what are called valuations, which is the stock price times the number of shares outstanding. Some of them are in the multiple billions of dollars. But their revenue, if you ask them what their quarterly report are, the revenue is maybe a few million here, a few million there. So there's a lot of excitement. People will say that there's a lot of hype, and people are just getting too excited and overvaluing these things. We'll see. One thing that you can't reduce to a mathematical formula is the stock market. People will make investments based on their emotions. Okay, so I talked a few minutes ago about use cases. How do you use these things? Where would people want to use these? And here's some more specific examples. So there's a U.S. government agency called DARPA, DARPA, Defense Advanced Research Projects Agency. That was actually the group that U.S. government agency that originally funded the internet. So they have a very, very good track record of looking at the future technologies, making investments, and encouraging companies and universities to research this stuff, and companies to develop products for those industries. They actually have a very big program called the Quantum Benchmarking Initiative, where they now have 18 different companies in a horse race to try to develop a quantum computer over the next few years. But they have mapped out, go from here, they have mapped out some use cases. And the interesting thing is, they've taken those use cases, like RSA or protein binding, rocket fuel propellant, Fermi-Hubbard dynamics. And these are corrosion-resistant materials, very specific things that would have huge economic value. And the question is, okay, well, this is great, but how big of a quantum computer do I need in order to be able to start solving that? And they've mapped it on this little chart here. This shows the number of qubits. Remember I said that today people are maybe at the 100 or 200 type of level. So this is where we are today. But at the same time, this is the number of what are called gates, which would translate into the number of quantum operations, which is a function of the fidelity. Remember I was talking about 99% or 99.999%. Well, this is sort of a translation of those numbers. And this gives people a target that says, look, we're here right now, and sort of yellow, maybe even here at the very bottom is where we are today. So this gives a target to all the manufacturers
that number one, they have to increase the number of qubits that they have in their system. And number two, they have to continue to increase the quality of the qubits as well as the effectiveness of the error correction code, so they can start doing these various applications. So still a long way to go, but
the industry is making progress. So the types of applications that we think are good, I think the biggest one, the one that will have the most impact on society over the next several decades, is a broad area. I call it computational chemistry. Think about, let's say there was a new virus, we'll call it COVID-2 or something like that. And the Pfizer's and Moderna's, they'd like to develop a new vaccine or new drug that will combat that. In theory, what they could do is they know the structure of the viruses. But what you have to do is you have to design a drug that combines with it such that it makes it inoperative, I guess would be the word. And what that is called a computational simulation. What the chemists would like to do is they would like to take any material, any molecule, and they would like to simulate how it reacts with another material. And that's, of course, I talked about it in drugs, but it's also in battery chemistry. We all know that electric cars are a big deal. Electric cars are built on batteries, and the manufacturers are experimenting with, should it be lithium manganese, lithium iron, lithium phosphate, they're trying a lot of different chemical combinations. And the problem they have is a lot of it is done by trial and error, because they would like to just simulate it, just throw it, put the problem in the computer, say, here's a compound, tell me how well it works, tell me how fast it charges, tell me how many kilowatt hours it can store, those types of things. Tell me about what the lifetime is. But they would like to simulate that, but the classical computers, they basically know the formulas, they know the physics of what it should be, but there's so many elements, so many atoms in these molecules that they can't simulate it on a classical computer. So what they end up with is a lot of trial and error. And that's how drugs are discovered today, is these chemical companies, they have a library of like 1 million different drugs, and a new disease comes along, and their biologists will take a guess. Well, maybe we should try these, or maybe try those. And they may start with maybe 10,000 or 50,000 drugs. They put them all in a test tube, see what happens. And they gradually come up, see which ones are doing better than others. And they gradually comes down. It takes, to develop a new drug these days, takes multiple billions of dollars and more than 10 years to develop a new drug. So there's tremendous, if you can cut that down by simulating something as opposed to actually having to try it out, empirically in a test tube, that's going to be big. We've talked about AI and machine learning. That's big. The finance industry, there's something called portfolio optimization. There's risk analysis. Every time you apply for a credit card, for example, the bank will look at your credit history. They'll look at 20 different factors. What type of credit line should I give this guy? That's a computational intensive problem, and quantum people are studying how quantum computers can help that. Logistics and scheduling, that's basically things like the traveling salesman problem that I talked about. It's also factory scheduling. If you have a factory and you're building things, and you have maybe 50 different machines, and you have 20 different jobs that you want to run through that, how do you schedule it so that you can finish all those jobs as quickly as possible. I talked about drug design, cybersecurity and code breaker. I have another slide. I'll talk about that, as well as people are looking at using quantum computers to develop chips, both semiconductor chips and other quantum chips. That can be, there's a lot of computers used when you design a chip, and maybe quantum computers can accelerate that too. So this is an example of computational chemistry, catalysts. One very, very famous problem is, how do you create fertilizer? So fertilizer is used every day, and you know, it supports, if we didn't have a process for building fertilizer, then the population of the earth would be about 1/10 of what it is today. It's used everywhere. And that process to create what's called ammonia-based fertilizer was invented 100 years in Germany. It was called the Haber-Bosch process, where you take nitrogen and I can't remember what else, maybe hydrogen, and you put it in a vat and you put it under extremely high pressure, very, very high temperatures, and that will create a reaction that will create ammonia. And the ammonia can be used as a fertilizer. It turns out that somewhere between 3 to 5% of the world's natural gas is used just for that one thing. And the thing that really bugs some of these quantum scientists is that plants can do that on their own, and they don't need natural gas to do it. They use some type of quantum process. We don't exactly know what that is, but there's a big quest right now to come up with a quantum computer that can figure out the formula, figure out the secret formula that could create fertilizer without requiring so much natural gas and heat and pressure. And that would, again, have a very, very big impact on society as well as, of course, the climate. I talked about battery chemistry, drug discovery, materials design. So computational chemistry, as I said, I think long-term, this may have the largest impact on society. Machine learning, there's this things called Boltzmann machines. I won't get into it, but if you use AI, there's this thing called training an AI, where it looks over all the data that you give it. You know, things like ChatGPT uses the World Wide Web as the data. That is a very intense process, and we believe quantum computing can help accelerate that. Again, finance, banks have a lot of research going into this. There's portfolio optimization, currency arbitrage, credit scoring. This is the foreign exchange markets. How are you able to use what's called arbitrage? And you know, the thing about banks is that if you can come up with a quantum program that gives you like 1/10 of 1% advantage over the way a classical computer is doing it, if you're running a portfolio of $1 billion or $10 billion, that 0.1% means a lot. and that's why banks are really have teams that are looking at how to use quantum. Okay, I've talked about logistics and scheduling. One that's actually quite local here. If you've ever been to the Port of Los Angeles and you've seen all those cranes, you know, you see those ships that come in, and what happens is those ships all have the I can't remember those boxes, those containers, those big containers. There's these giant cranes, and you can see them if you go, you know, like to San Pedro or the Port of Los Angeles. The crane will come over, it'll take the storage container and it'll put it in a yard initially. And Then later on, maybe a couple days later, you have a line of trucks that are coming in, and each truck is going to pick up its individual load. And it turns out that it is a computational intensive problem to figure out how to do that in the optimal way. Because what the people at the port were doing originally, it was basically first come, first serve. Let's say there's a line of trucks, truck number 1, 2, 3, 4, 5. They go to truck number 1 and say, okay, what container do you want? Oh, it's over here. And the crane would have to move over, pick up that up and go there. And then truck number 2 says, oh yeah, I need my container, and it's on the other side of the yard, and the crane would have to go over. And it turns out that if you're smarter, you could save a lot of time. Let's say truck number 1 needs a container on the left side of the yard. Truck number 2 needs a container on the right side of the yard, but truck number 3 needs a crane that's right next to the one that was used for truck number 1. So the smart thing to do is you don't do it in a first come, first serve order. You do truck number 1, and then because truck number 3 needs something right next to it, you do truck number 3 next. And you save a lot of time moving those cranes. So a company had figured out how to use quantum computers for that. That's an example of some of the logistics types of things that people are using, want to use quantum for. So I was talking a little bit about money and dollars, and let me just throw some numbers at you. This is a graph, again, from our intelligence that shows the overall value of the quantum market. And again, people are always interested in how many dollars you're going to make out of this. And the interesting thing is that our model actually splits these dollars into 2 different types. There's the dollars that the quantum industry need, these companies like Amazon and IBM and Google and whoever else will make by selling quantum computers or selling services or selling software. And again, in the long term, again, this is like in 2050, 25 years from now, our estimate is at about $290 billion per year. But the people who are actually using the computers, these quantum computers, all those use cases I was just talking about, they're going to make like 3 times that amount in terms of the sales of the new drugs or the amount of cost reduction that they have because they're running more efficiently. So it's something where the end users are going to benefit much more than the people, although both parties are going to benefit a lot. Today, we're talking, and today we're in 2025, so it's maybe the value of that is 1 to 2 billion because the market's so immature, but you can see how this grows over time. And it's going to be a large business, not the largest, will never be as large as, for example, the classical computing business, but it'll be a very significant business. Okay, and here's the last section. I'm going to talk a little bit about implementation steps. This is some of the advice that we give to some of our clients. And if any of you are out there and thinking about how you could use or what you should do to take advantage of quantum for your companies, let me give you a couple pointers. So the first one, I might title this slide Defense Before Offense. One of the things I didn't get into is the fact that quantum computers also can represent a threat. As we all know, all the transactions we have on the internet use encryption. If I want to buy something on Amazon and I type in my credit card number to Amazon, I don't want someone tapping into my phone line, stealing my credit card number and starting charge. So what was implemented a long time ago on the internet is encryption technology. Uh, we do this thing called key exchange. I then take my credit card number, I encrypt it, I send it over, and I have a key and Amazon has the key. I can send it over, and even if someone taps my phone line, they won't be able to use my credit card. It turns out that that is based on what's called a one-way mathematical problem. Some of the key codes that we use today, which is factoring a large prime number. If you have a number that's 2048 bits, and it's a prime number, or it's a number that only has two factors, two prime numbers that are factors. If I give you the two prime numbers and you multiply them together, that's easy. Computers can do that, in a few nanoseconds. But if I give you the overall number, the 2048-bit number, and say what two factors were used to create that, that is a very, very difficult. That's one of those problems that, again, is exponentially hard for a classical computer. If it's a number like 15, classical computer says, oh yeah, that's easy. It's 3 times 5. But 15 is only a 4-bit number. At 2048 bits, it just can't be done on a classical computer. Someone, a professor about 25 years ago, 1995, a guy by the name of Peter Shor, came up with Shor's algorithm and said, if you give me a large quantum computer, I can do it. And we know what the algorithm is. We know exactly what we need. We know how many qubits we need. We need something like a million qubits. And the problem is, the threat right now is that we believe that people will have that million qubit quantum computer probably in the next 5 to 10 years. So if, the Chinese or someone like that develop that, our entire internet is at risk. So there's a lot of governments, very, very concerned about this. And there's a government agency called NIST, N-I-S-T. It stands for the National Institute of Standards and Technologies. They ran a competition, and they've selected about a half dozen new algorithms to replace the factoring of the number that I was talking about, that they are telling people you should start using these to replace what was called RSA encryption, which was based on the factoring thing. So if you're in a company, if you're an IT manager in a company, our first piece of advice is start now. The algorithms are here, but what you're going to have to do is you're going to have to upgrade all your systems to use the new algorithms instead of what you're using today. And a lot of companies out there that'll help you do that, but it's a complex job. 25 years ago, there was this problem that maybe some of the senior people here might recognize called Y2K, where the dates, originally when people used computers in the 1960s, 1970s, they would have a form and they'd only use 2 digits for the dates, 97, 98, 99. And all of a sudden they said, when we go to year 2000, computers are going to get very, very confused. They're going to screw up. And people had to upgrade all their software to go from 2-digit years to 4-digit years. And it sounds crazy, but at the time, people were predicting that trains would fall off their tracks, and the entire, electric power plants would shut down, and all sorts of things, because the computer systems that ran these things would get confused. Well, you have something somewhat similar. We call this Y2Q, with years to quantum. So the first thing is you have to upgrade your system to use these new algorithms. And again, if you want to see me afterwards, I can talk to you more about that. But This is sort of, what you might call the bad side of quantum computers, where quantum computers in the hands of a hacker can really represent a threat. But, as I was showing earlier, there are a lot of opportunities in all sorts of industries in order to leverage quantum computing, and in order to be able to come up with new programs that will either save money for you, help you develop new products. And what our company has come up with is this basically a 4-step process, where the first one is to discover a little bit about quantum computing. Maybe the first step is listening to me, this talk here, but understanding a little bit more about it, how it might apply to your mission. How do you discover what the potential use cases are? You go through the list of prospective use cases, you start evaluating them a little bit, and you start figuring out, well, which ones might actually work, which ones should I use? And I have more detail on each of these steps. I won't go into tonight, but again, if you see me, I can send it to you. And then many companies, like the finance companies and drug companies, are at the stage right now called execute. They have put together small teams. Small teams are working with vendors like IBM or Google or Microsoft or whoever, and they are developing what are called proof of concepts. They're actually looking at various things, planning how they could use that, and then they develop an application, a quantum application that they think will work. And then the last step is incorporate that into your organization. And it turns out that these big companies, even introducing a new classical program is always a challenge. So you have to figure out how to integrate this new quantum program with your IT infrastructure. You have to learn you have to train your people on how to do that. You have to test it and figure out, can I make future improvements? So there's a 4-stage process that people have to go through, but we do believe that many companies should start doing this now, because as I said, in the next 3, 4, 5 years, the quantum computers will be much larger than they are today, and it would be, at least theoretically, it would be possible to create an application that shows this thing called quantum advantage, but you can't do it overnight. You can't do it in 1 month. You can't do it in 2 months. Developing these new applications inside of a large organization takes years. So, that's sort of my quick summary of this. I could talk for the next 5 days about quantum, but we do think that the quantum hardware and software, it's improving rapidly. We have many different systems available, both NISC and fault tolerant. We think initially just a few special cases that can run without the error correction will become possible. And then once the error correction comes in, then even more, and the industry will grow exponentially, as I was showing with that revenue curve before. Now there's some that will take a while. There's some applications that we've looked at will take 20 million qubits. So you won't see those next year, the year after. Maybe in the 2030s you might see that, but users will need to do that. So our advice is to keep abreast of developments, be flexible. It's a very dynamic, changing very rapidly, but it will have a great impact on society. For those people who participate in the industry, either as a provider, working for a company that supplies quantum computers, or as a user, I think there could be very, very significant benefits. So, so just the last word, I'm almost done. I'll take questions in just a second. I want to quote something called Amara's Law, sometimes quoted by Bill Gates, where When you have a new technology, people will typically overestimate how great it is. And we're starting to see that, quite frankly, now. There is a lot of hype in the quantum industry, but longer term, people will underestimate its impact. And basically, if you study the history of AI, I think AI was a good example. People were talking about AI in the 1980s, 1990s. They were here. It took a long time to come to fruition, but now, we're sort of maybe right here with AI. I think some more things will happen in quantum. So with that, if you have more questions, you can view our website. It's globalqi.com. And our business, again, is to help people to be successful in quantum, either as a provider or an end user. And with that, I think we're open for questions.
Yep.
Yes. Let's go here.
Yeah, there's a woman there.
I'm gonna,
Right.
before you ask your question, let me give you the,
Oh, okay.
Yes. Hi, I'm Leslie, I'm a grad student, and I wanna be rich someday playing the stock market. So if you're analyzing all these companies, you're watching them, play the market, do you have a good stock tip? Everybody who's $4 or $5 right now that I can get in on that you think will be big?
So, yeah, I'm actually asked that question by people from Fortune Magazine and Investors Business Daily and those things. I get questions like that almost every week. And here's what I tell them. They don't like the answer. Everyone wants the magic stock chip. Quantum is a very, very dynamic industry. And it's, as I said, it's like a horse race. And the company that you think might be a leader now, some guy may come out of left field and come up with a better way of doing it and completely overtake them. We're seeing that, example, if someone said, okay, well, Intel is a great company. 5 years ago, if they said Intel was a great company, they make all the microprocessors, I'm going to invest a lot of money in Intel. And what happens? AI comes along and NVIDIA completely overtakes them. So my advice to all these people who ask me that question, I says, I do think quantum will be a good industry. Putting all your eggs in one basket is very, very risky. If you want to make an investment, there are like 5 or 6 companies, and I would invest in the market basket, a little bit of money in each, and that reduces your risk significantly.
There's an ETF, you want to bet on all of our systems, there's an ETF called QTQM, which is a way to bet on all of ours.
There is an ETF. Yeah, the only problem with that ETF is it has a whole bunch of non-quantum companies in it too.
So earlier in the slideshow, you showed the merging number of qubits, right? But when you increase the number of qubits, you also increase the thermal and energy challenge of that. How do you think these companies are going to address them?
So one of the things we think will happen is that the quantum industry will go and do something very similar to what the classical computing industry did, is they will build quantum computers as modules, and then they will create a network of modules. And the PsiQuantum company that I was talking about, they are building, I don't know, maybe 1,000, 2,000 equivalent qubits in a module, and they connect maybe 100 or 200 or 300 of these modules, but with fiber optic. And they're able to use multi-processing in order to solve the heat issue, because you can have a new cooling. Well, it depends on the technology, but if it's superconducting, for example, there's this thing called a dilution refrigerator. You have one dilution refrigerator for each module. PsiQuantum, They are building the world's largest cryogenic facility. That's what's happening in Illinois. Huge amounts of liquid helium, this really, really large facility. That's where part of the $1 billion is going to. But that is being used to cool each of the individual modules. Heat is a big issue, and that is indeed one of the limiters that we see. And the reason is it's not, it's because qubits, I said qubits have this reliability problem, and reliability problem gets a lot worse as you get hotter. That's why a lot of these systems, they will use these very, very special, very expensive refrigerators called dilution refrigerators to cool down those qubits to 15 millikelvin. Just 15 thousandths of a degree above absolute zero. It's 1,000 times cooler than outer space. So that's one of the techniques that people use to solve this reliability problem. But in some cases, like I've seen IBM's roadmap, they're going to have systems that may have 50 or 100 or 200 some odd dilution refrigerators to do that.
Do you see the possibility of moving some of this quantum computation to space?
Not right now. I actually have a friend who's working to build an AI data center in space. But the problem is these systems are so finicky that if something goes wrong, how are you going to repair it? It's not going to be easy. They're just trying to get something that works right now on Earth. So, maybe in the year 2100, the systems are large enough and reliable enough that they see some value in putting it into space. But I don't think it will happen in my lifetime. But well, actually, I will take that back. What will happen is I talked about quantum communication, and I didn't talk too much about it, but you can create a quantum network where you take these qubits and you send them as photons over fiber optic cable. But you can also send these photons up to a satellite and have it bounce back. And people are talking about creating encrypted networks that way. Boeing, for example, has a big experiment. We've written about Boeing. I know the guys at Boeing who are doing that. They are building what's called entanglement in space, but it's only for communication and not for computation.
Do quantum computers, have you ever seen one that's not plugged directly into a wall, but it has its own, two questions, its own power source like a battery, and then like in terms of time to like warm up and actually run problems, does it take a long time to, from like flipping the switch to it actually having capabilities?
Okay, so I've never seen a quantum computer run on a battery. Again, they run, some of them run on 110 volts or 220 volts or something like that. They bring in power from the power company. The nice thing about quantum computers is typically they do not consume as much electricity as the data centers. And actually, one of the benefits that people believe they can do, if they can do something on a quantum computer that they could also do on a classical computer, but the quantum computer can do it with a lot of electricity, that might be a reason that people might switch, even if it's not faster. With regard to cool down time, that's a very interesting problem. I just mentioned that they have these special refrigerators that, can cool the system down to 15 millikelvin. So if you're at one of these companies, let's say you develop a new chip, you have to open up the computer, bring it at room temperature, you put in the new chip, you close it up. It'll take a couple days for that refrigerator to cool it down from the room temperature 70 degrees to the Fahrenheit to 15 millikelvin. It'll take a couple of days for it to cool down. So as a result, people try to avoid that as much as possible. And they try not to do that unless they really have a new chip that they think is going to be good.
Based on the growth patterns that you've seen so far, what do you think the quantum analog to Moore's law is going to look like?
It's going to be very similar. But I think it's going to be similar in two ways. You know, Moore's law only talked about the number of transistors doubling every year, every 2 years, that type of thing. And again, we're seeing something very similar to that. You can look at the roadmaps that we publish on our website or on the quantumcomputingreport.com. And again, people are 100, 200 now, and they're talking about 1,000 qubits or even 10,000 qubits. And there's one company called IonQ just announced they're going to have 2 million qubits by 2030. That's only five years away. That's faster than Moore's law. But the other thing that quantum will have that was not included in the classical version of Moore's law is the increase in the qubit quality. Again, people are going to take that 99% that I was talking about and take it to 99.9%, 99.99%, that type of thing. Those quality metrics are also increasing too. So there is somewhat similar, whether it's the exact same formula as Moore's, I can't say, but we are going to see similar phenomena.
We're gonna have to get one more question here and then one more over there, and then we're gonna have to wrap up because I think we're past our time already. So.
Hey, thanks for the talk. You discussed some algorithms that maybe use 1 million qubits, 2 million qubits. Are there algorithms or examples you can think now that could use under 100,000 qubits? Or are there applications for like smaller qubit quantum computers?
There are a few, and I don't think I had any of those charts, but we think perhaps a few types of chemical simulations you might be able to run those with 100,000 qubits or less.
Thank you very much. You showed a slide that was showing the algorithm needs to improve and also hardware. What do you see in the hardware side that needs to be improved, and what are the limits? So is this the temperature, or is that the challenge in manufacturing of the hardware? What are those challenges? What are the limits?
So the first is scaling. So here's a problem that the engineers are working with on a basis. So I talked about the number of qubits. In, let's say, a superconducting machine like the ones that IBM and Google have, each of the qubits needs wires to control it. Each qubit needs something like 3 wires to control it. And today, if you look at their systems, what they have is they have outside this dilution refrigerator running at room temperature, they have electronics called arbitrary waveform generators that develop various pulses, microwave pulses. They have to string cables from that external electronics down through the dilution refrigerator to the chip, eventually to the individual qubit, so that it control the qubit, so that it can do the various operations that the qubit needs to do. So, you know, if you have 100 qubits, okay, 3 wires per qubit, okay, that's 300 wires. I can do that. You know, they've come up with cables to do that. But let's say you have 10,000 qubits. How are you going to string 30,000 wires down like that? So what they're working on, actually, is I saw a presentation on it today, this morning, is they're developing semiconductor chips that can run at those very, very low temperatures. You know, most of the chips, you know, like the you know, the microprocessors from Intel or from NVIDIA or those types of things. What happens, you try to run them at too low of a temperature and they just flake out. They won't work. But people are developing special chips. And what that allows them to do is they can take just a relatively small number of wires from that external control, you know, maybe a dozen or a couple dozen, send it to the chip. And the chip, though, is sitting right next to the qubit chip. And then they can use, you know, ball bonds and or chip stacking in order to solve that problem. So that's an example of the types of problems that people have. The other one, again, relative to scaling is, you know, in the semiconductor business, the more qubits you have, the bigger the chip you have. It's called die size. And it's hard to control the uniformity. As a chip gets larger, it's hard to control the uniformity when you deposit layers or those types of things. And that's one of the issues you have, is that if the chips in the middle might work good, but the chips on the outer edge, they may not work quite so well. So they have to solve those problems to make those chips on the outer edge work as well as the chips in the middle.
Okay, well, thank you very much. Let's give our thanks to our speakers. And what we're gonna do right now is thank our speaker more formally,
Okay.
because we have a little
Oh,
gift here. This one here, this is for Mr. Doug Fink.
Oh,
of
thank
Global
you so
Quantum
much.
Intelligence,
yeah.
and okay.
1, 2, 3, and one more. Okay, thank you.
Okay.
And we will hopefully see many of you in Pasadena next month. We'll take a break in December and hopefully be back at UCLA in January. Oh, wait, Mr. Nino, could you come up here, please? Martin, Nino, can you come up here, please? Yes, you, right now? I know you've been very busy and I know you had to take care of the students because it's late in the evening and they have to be somewhere. But we want to also thank the Samueli Academy and you as their representative. We have a 1-year OSSC website sponsorship
Oh, well.
for the Samueli Academy. That's now worth $500.
Oh, man.
So we
Thank you very much.
Thanks so much. All right, thank you. Thank you, thank you.
Thank you.
And if I can ask you guys to throw away in the different trash and
Yeah.
recycling containers, that would be a big help. And if you have questions, I think Doug, you might still be around for a little bit. And we'll see you again soon.